if you have trouble figuring it out, because like there are other kinds of solutions like alloys and things like that, the solvent is the substance with the greater percent mass. Unsaturated. So we got three basic terms to describe solutions. An unsaturated solution means more solute can be dissolved. Okay? So if you have an unsaturated solution and you drop a little bit more solute in it, stir, it will dissolve and disappear. A saturated solution, at whatever temperature it's saturated at, you can keep it at that temperature and just add more solute, it won't dissolve. So if you put a couple of crystals in and stir, it'll just sit there. Now, a supersaturated solution is weird. It actually contains more solute than should be able to dissolve at that temperature. It's unstable and it won't stay that way. And if you add a small crystal of the compound to it, the whole solution will turn solid. Now, you can pop up the video if you go back and get the original notes instead of looking at this video. There's a link to the supersaturated solution video. Now, this is the solubility curve. All right, it's a solubility curve basically shows how much of a solute will dissolve at different temperatures. Since this is water, we went from 0 to 100 degrees. And solubility is measured in the units of grams of solute per 100 grams of solvent. The solvent in this case is water. What do the lines represent? I'm going to talk about also the way their direction. The line is the line of saturation. In other words, that is the most you can normally dissolve at that temperature of the compound, in this case at 100 grams of water. Take a look at all the compounds that go up. If you look at their formulas carefully, you will see they are all ionic compounds. So, ionic compounds are considered endothermic. If you were to put them in water and stir, the water gets cold, and more will dissolve if we heat them up. Okay, so you can see that solubility increases with temperature. The ones that go down, hydrogen monochloride, ammonia, and sulfur dioxide, those three are all gases, and they represent what happens with every gas. Any gas that you try to dissolve in water, as the temperature goes up, less dissolves. So, and we refer to that as having an exothermic heat of solution. If you try to force it into solution, you can make the temperature go up, but we don't need to worry about that very much. The key thing here is that since all gases, there's less of them that dissolves at high temperature. You could imagine that if the oceans warm up significantly, several degrees Celsius, the amount of oxygen that's dissolved in the water will go down, and that will make it harder for fish to extract the oxygen from the water with their gills. The other thing is that scientists tend to pick one condition to compare things. So not only did they pick grams of solute per 100 grams of solvent as their units for solubility, if they wanted to compare, several scientists, the solubility of a compound, what I gave you. This is not homework, but it is something you could look at. So I'm going to give you some examples of how to read the graph. Again, remember the lines represent this most you can put in. That's the line of saturation for these four substances. Three of them are ionic and they increase with temperature. One is a gas that decreases with temperature. What are the units for solubility? Again, grams solute per 100 grams of solvent. And if we were a scientist sending that data to somebody else, we'd probably give them the number at 20 degrees Celsius. Now let's take a look at a couple of the problems and see how we would solve them. What is the solubility of KCl at 50 degrees? So we find 50 degrees, we go up. Remember, the line is the line of maximum solubility for the curve. So for KCl, we see it crosses at 50 degrees at maybe like 42, 42 or 43 grams per 100 grams of water. So that would be our answer, around 43 grams of potassium chloride per 100 grams of water is the solubility. Now look at number 10. If 40 grams of KCl were placed into this 100 grams of water at 60 degrees, then stirred, what kind of solution would we have? Again, this is checking your vocabulary. Here is 60. Let's go up and find out how much will dissolve at 60 degrees in 100 grams of water of KCl. We see at 60 degrees about 45 grams will dissolve. Well, we only dissolve 40, so this should be an unsaturated solution. We can dissolve just about 5 more grams, and then we get to a saturated solution. Okay? Right now it's unsaturated. Okay, so we're going to be doing graphs. We have a lab. We're going to be doing graphs. We'll spend some time reading them and figuring out how to use them. I just wanted you to take a quick look at a solubility graph so you understand a little bit about what it's trying to show you. Now, factors that affect the rate of dissolving. 3 factors that affect the rate of dissolving are all kind of the same in a way. They all involve having more solute and solvent molecules hit each other. So if you stir, like for instance, take some iced tea, put in a spoonful of sugar and stir, you're going to see that it's going to dissolve quicker than if you put in a spoonful of sugar and don't stir. Heating also will increase the movement of the particles, both the solvent and the solute, and you'll get more collisions. So again, with more collisions, it dissolves faster. So again, your sugar would dissolve faster in hot tea than in cold tea. And finally, increasing surface area increases the speed of dissolving. Now that's a little harder to understand, but if you think about it, if you took a sphere of something that you were trying to dissolve, a solid sphere of sugar, or if you grind that solid sphere into powder, you're going to find out that the powder, which has more surface area, even though it's the same mass, will cause more collisions between the solve this problem, how many moles of sucrose are in a half liter of a half molar solution? What we would do is solve for n, we're given molarity, and we're given the volume, and then we'll know the number. So we solve for n, so it's just molarity times volume in liters, and when we multiply it out, we get 0.25 moles of sucrose. Because we only have one sig fig, it would round to 0.3 moles. Okay. Now, if we want to prepare a solution and we start with a solid, I'm going to give you a really handy formula that will help you figure it out how to do it. Here's the formula again. Write this on the top of practice problems 15-2. Grams of solute that are in that solution will equal the molar mass of the solute times the molarity of the solution